the first section. Does anybody have any questions from those? Take a minute, deal with those if there are any. If there's not, that's cool. Or if there's just not right now, that's cool too. We can always come back and look at it later. Sophia?
Can you do 21, please?
21. So, first thing, we'll find those vertical asymptotes, setting the denominator equal to 0. We just get 1. Next thing, we find those x-intercepts, setting the numerator equal to 0. We get just the point 0, 0. The y-intercept, again, we're plugging 0 in for x. We get just the point 0, 0. You see that the y-intercept and the x-intercept are the same in this case, and that's okay. And then if you look at the asymptote end behavior, we notice the degree of the numerator is greater than the degree of the denominator. So to find the asymptote, then, we need to do polynomial division. Since the denominator of this fraction is monic, has degree 1 and leading coefficient 1, I can use synthetic division here, which is what I would like to do. So I have a 1 in the x squared's place, no x's, and no constant terms. And then if I run my synthetic division, I get this. So remember, starting at the far right, it goes remainder, constant term, x coefficient, x squared coefficient, etc., etc., etc. So just the first two numbers are the pieces that I care about, and that gives me the asymptote y equals x plus 1.
I just have a question on the y-intercept. Like, why is it not, like, undefined? Does that make sense?
0 over negative 1 is 0.
Oh, instead, just kidding, I thought it was okay, yeah, that's good.
So to finish this out, we'll just kind of draw our asymptotes and plot. Probably we'll have to do a little bit of look at a little bit of the limits here, but depending on the situation, maybe we can get away with not having to do that. So, vertical asymptote here. And then to graph y equals x plus 1, I just need 2 points because that's a straight line. So I'm going to use the y-intercept 0, 1 and the x-intercept negative 1, 0. But you could do anything you want. And I'll plot my x and y-intercept there at 0, 0. And I can tell right away, without actually having to do any limits, what's going on the left side of my vertical asymptote, because I know I have to go through this intercept. I can't start from the positive and go through that because I'd be crossing this oblique asymptote. So I know it's got to start from the bottom. So I know that I'm going to have something that kind of looks like this. But the other side I do need to check the limit on. So let me pull up my calculator and do that. So I have, let's do fraction. X squared over x minus 1. And if you check the limit on the left side, like, it's no big deal, you get the same result. So like it's not a big deal at all if you decided to do that. So let's check on the right side, so something a little bit bigger than 1. I get a positive. Just to make sure, let's get a little bit closer. And more positive, so I'm quite certain that that my should be starting at the top there. I'm doing one of those. Cool with that, sulfurs? Other questions? Jacob?
You do succeed.
Sure. So first thing I would do is check to see if there's any reducing I can do, since it seems pretty obvious that there's a bunch of factoring that can happen here. So the numerator is a difference of 2 squares. And the denominator, I can take out a greatest common factor of x, and then things that multiply to give me -8, and add to give me -2 is -4 and +2. So there's no reducing to do, which is fine. So setting the denominator equal to 0, my vertical asymptotes are at 0, 4, and -2. Setting the numerator equal to 0, my x-intercepts are at 1, 0, and -1, 0. My y-intercepts are none, because if I plug 0 in for x, I get something over 0. And then if I look at my asymptote end behavior, the degree of the numerator is 2. The degree of the denominator is 3. Since 2 is less than 3, I know that we have the horizontal asymptote y equals 0. And that's all of my little key features there. So it's time to start putting the graph together. Now on this one, I almost certainly will have to do some limit checking, because we have a lot of asymptotes going on there, but that's okay. So we have this one at -2. We have this one at 0. We have this one out at 4. And then we have this horizontal one here at 0. And then I have x-intercepts here. And now it's time to go and look at my limits. So I have to look at each of these limits. There's nothing, I can't make any conclusion with this one based on where the x or y intercepts are, which is a bummer, but you know, like sometimes it just gotta be that way. Go ahead and put that in. Just on the left side of -2. So that's negative. We'll get a little bit closer just to be sure. More negative, so I'm pretty sure then that this piece is going to be like that. Okay with that? And we'll check on the other side of -2, the right side of it. So that's positive. Get a little bit closer just to be sure. More positive. So I definitely think I'm going to be like, so I'm going to definitely starting up here. I'm going to go through the asymptote, or go through the intercept, go through the other one, and now I know that I'm going to have to do this, because I can't go through this and then turn around and go back down. Well, I guess I could have a bounce there. Oh, no, I can't because it's not a double root. Right?
And these go through the vertical asymptote.
Oh, crap. I screwed that up, didn't I? I forgot about the vertical one at x equals 0. So this has just got to be like this. Sorry. And then this side, though, I have to check the right side of 0. The left side of 0, I'm quite certain that that's what's got to be going on. Since -1 is a single root, it can't bounce and go back the other direction. It's got to pass through and then just keep going down. Oops. That's positive. So doing the other side of 0, that's positive. We'll get a little bit closer just to make sure. Still positive, so that's good. And OneNote froze on me. This has been, we got these new computers or whatever, and this has happened to me, maybe a dozen times per class. Yep. And I've even ended the task on my OneNote. It's pretty start. I don't know why it's doing that either. I can't figure out like what it's doing that kind of gets it all bajiggity on me, but it's doing it. Anyway, so this is positive, and it's has to go through this x-intercept. And then I know since it can't cross the x-axis again, it's got to do this, right? It can't be a bounce and go back the same direction because it's not a double root. So I can do that and skip having to check the left-hand side of 4. Although you can certainly do it. There's nothing wrong with checking it. You know what I mean, guys? Just talking about saving some buttons, pushing. And then we'll check just the right-hand side of 4. And that one looks like it's got to be the top or the positive side of it. So we have those.
So are you allowed to cross the horizontal asymptote.
Well, only if there's an x-intercept.
Alright.
And just to be clear, we call these asymptote end behaviors because not all of them are asymptotes, right? Like, it's going to act asymptotic at the ends, but in the middle, maybe we have some places where it can cross. But we'll catch those with the x-intercepts.
Alright.
So, if you have an x-intercept on that, it's okay to cross it because you know it has to, because you have the x-intercept there. You know what I mean?
Yeah.
Cool.
Sorry, everyone.
I don't accept it.
How do you find, like, what's the formula to find, like, how to graph the horizontal asymptote when you have, like, the y equals x squared?
So that's not horizontal if it's y
Or
equals
the-
x squared.
Or the slanted one?
It's not slanted either if it's y equals x squared. It's going to be parabolic.
Okay, but how do you find, like, the points?
So you need to have the vertex of the parabola. And then I would require at least one point on either side. I think usually for this kind of an activity, the x-intercepts would be the best ones to get. So you can find the x-intercepts just by solving the quadratic equal to 0, which isn't so bad. You probably have to use the quadratic formula, but like, who cares? A decimal is fine. And to find the vertex, the x-coordinate is, well, for a standard form quadratic, which is what you would have, you can find the vertex by doing negative b over 2a. That would be the x-coordinate. And you can find the y-coordinate just by plugging that back into the quadratic.
Okay.
Is that enough?
Thank you.
Yeah, you're welcome. Anna?
Can you do 23?
Yeah, sure. So again, let's just factor this real quick to just make sure that or check to see if there's any reducing that we can do. There's not, so that's cool. And again, if I shortcut through anything that you're not comfortable with, you can holler at me and we can do stuff in greater detail, but I'm assuming that a lot of these little sub-skills you're fine with. But if I ever do something that, like, hey, you just did something real fast there, and like, how the heck did you do that so fast? That's definitely okay. So this is like negative 27 over 4, but I think I'd rather have it as a decimal. I guess I could have done that in my head. Well, it is 8 o'clock on a Thursday that I wished was a Friday, so. And then for the asymptote end behavior, again, since the degree of the numerator is greater than the degree of the denominator, this is a polynomial division problem. Thankfully, the denominator is monic, so I can just do this with synthetic division. Again, I don't care about the last number. Oops. So far, so good?
Yeah.
Okay. So let's get ourselves an axis here. Put some of these things on there. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have -4. And then y equals x plus 2. So I'm going to use the point, the y-intercept, so 0, 2. And the x-intercept, so that's -2, 0. There's that. And then I'll plot. Oops, I guess I need some more tick marks. So 3, 4, 5, 6, 7. So I have -0, -6.75, -9, 0, and I have 3, 0. And I would say with this, that's enough that I don't even really need to check the limits. So on the left side of -4, I know I have to be coming from the positive because I got to get through this x-intercept. And I couldn't do that from below without crossing that slant. So I have something like this. And then similarly on the right side of -4, I know I have to be coming from below to go through the y and the x-intercepts here. Because if I tried to do it from above, I'd have to again cross that slant. So again, I can get away without having to do that. So I get something that kind of looks like that. Does that feel okay?
Yeah.
And again, it's fine to check the limits if you're not sure, if it's not obvious to you by looking at it, like, oh, it has to be this way or that way. You can always check the limits.
Okay.
But I mean, that's just like less buttons for me to push, and if I can just hand wave and explain why I know what it's going to look like without having to get out the calculator, I'd like to do that. You know what I mean? Because I'm lazy. It's like less stuff to do. Everybody happy with this? All right. Let's get to the new old stuff. So again, this whole chapter is topics that we would have done in last year in our algebra course, but I'm going to redo again just to get a little bit of extra practice. So there's like a couple of different approaches that we can take to solving, but they really kind of break down into two notions. So talk about clearing fractions or making a global least common denominator. They basically boil down to doing the same thing. And there's other stuff that you can kind of do that's basically equivalent to doing one of these two things. And really, these are not, I would say, really dissimilar techniques. My personal preference is using clearing fractions unless there's an obvious reason why not to. But I think it's usually always going to be the fastest route, and I prefer to not have fractions. The benefit of doing the clearing fractions is the first step is you just kind of get rid of all the fractions in the problem, which is usually preferable for students. We typically don't like fractions. So let's just kind of go through and do some examples. I'll do some of varying difficulty to try to get a flavor for what to do here. And I'm just going to do these kind of all doing clearing fractions because I think it's really the most appropriate technique for these. But if some of you are like, yo, I used to do it this way, is that still okay? It probably was. You know, if you're real concerned, you can always come and ask me about it. We can walk through, and I can tell you the pros and cons of what you're doing, or even if it's appropriate or not. I'm happy to do that kind of thing. So the idea here with clearing fractions is I want to look at every fraction in the problem and then multiply both sides of the equation by the least common denominator of those for those fractions. Here that should be really easy. There's only one fraction, only one denominator, so the least common denominator is just x. Everybody cool with that? So we just multiply both sides by x. So when I distribute through, I get x squared plus 3 equals 4x. Pretty cool? What I'm left with now is a quadratic equation. So to solve a quadratic equation, I have to make it equal to 0. So I'll just subtract the 4x over. And then my two primary quadratic solving techniques are going to be either factoring or using the quadratic formula. Typically, in a case where the leading coefficient is 1, like this one, I'm going to at least try to factor it first. And if I can, I'd prefer to do that, although I know that not all of them are factorable, using that factoring technique, or that shortcut factoring technique. But this one is. Two numbers that multiply to give us positive 3 and add to give us negative 4 are negative 3 and negative 1. And when I set each of those factors equal to 0 and solve, I get x equals 3 and x equals 1. I'm not done though, because it is possible to get extraneous solutions here. So I do need to check my answers. Although I don't need to do a full check of my answers. I don't actually need to make sure that both sides are equal. All I need to do is check to make sure when I plug my solution into the denominators that it doesn't make a 0 denominator anywhere. And here, since the denominator is just x and my solutions are non-zero, clearly they're both fine, right? But I do need to at least make a brief check to make sure of that. So let's do another. And again, my plan here is just to do several examples and then go on about our business. This is a pure technique section, and there's no kind of theory involved. And just kind of doing some practice problems to give you a feel for what's going on. So again, clearing fractions, I'd want to multiply by the least common denominator of all the denominators, which in this case would be, okay?
X minus 1.
I think you mean x plus 1?
Wait. But doesn't clear up the denominator, like, it says 6 over x plus 1, so multiply by x minus 1, then it would parse it out.
Nope. So you just need x plus 1 here. I think you're getting turned around with multiplying by a conjugate that we would have done for, like, getting rid of a radical from a denominator. But here all we need to do is the same thing, because when I multiply here, the x plus 1's cancel, right? One from the top cancels one from the bottom.
Oh.
Because we're multiplying by like this over 1, right?
I see what you mean now. Because here it'd be 6x, 6 and then x plus 1 over x plus 1 and then 8 cross out.
Yes, precisely. Yes. So that gives me this, right? And then we'll multiply everything out. I'm left with a quadratic. Since the leading coefficient is 1, I'm going to try to factor this. It does factor. So my solutions will be -3 and +2. And if I go and I check these, do those both check out? They surely do. Right? -3 + 1 isn't 0, and 2 + 1 isn't 0. So again, that's all I care about. You can check the whole thing to make sure the two sides are equal. That's fine. But just more to do. Like if it's going to fail, it's going to be because you get a 0 denominator. So all you really need to do is check that. It's a little bit speedier to do that. And I'm all about trying to save your guys' time, you know. My time's valuable, your time's valuable. Nobody likes wasting their time when there's a shorter or quicker way of doing something. You know what I mean, guys? I don't want to keep that information from you. I want to share it with you. So here, it's a little bit tough to see what the least common denominator is with the way this is currently written. But if I factor all the denominators, it's much easier. So I would start by factoring the x² minus 4x plus 3. If possible, and it is in this case. And that makes life much easier, because now instead of thinking your least common denominator is x minus 1 times x minus 3 times x² minus 4x plus 3, it's just x minus 1 times x plus 1. Or x minus 1 times x plus 3. And minus 3. You know what I mean? Sorry about stumbling all over myself there. I need a little bit more space. I want to emphasize here that it is really important that you're using the least common denominator. Although it's fine to use any common denominator, you can make the problem a lot harder than it needs to be if you don't use the least common denominator. Because you've seen that polynomials get a lot harder to solve when the degree is, as the degree gets bigger. If you use a not least common denominator, you're going to end up with a polynomial with bigger degree, and then you might have to use the techniques from like last chapter to solve it, which is not a lot of fun versus ending up with like a quadratic that's pretty easy to handle. So just be cautious about that. So let's see, I multiply through, and I get this. Everybody okay with what I did there? Again, I did all the reducing and multiplying through in my head, which, again, if you need some explanation on what I did, that's okay. I'd be happy to do it again, but not unreasonable to show this amount of work and have it still make sense. Distribute things through. I'm going to combine like terms and move everything onto one side so that it's equal to 0, because I notice that I have a quadratic. Okay, here. And this time I notice the leading coefficient for my quadratic isn't 1. So rather than trying to factor this, because I know I'd have to do that long factoring or I have to do the grouping or whatever, I'm just going to use the quadratic formula, because to me it's probably about the same time, and I'm not even guaranteed that this is factorable. It is, but I would just use the quadratic formula in this case. So let's see, negative b plus or minus. Negative b squared is 25. And then 4 times 2 times negative 3 is negative 48. So minus a negative 48 is plus 48. I'm sorry, that should be 20. An extra 2 in there or something. Over 2 times 2. Actually, let's try. Okay, so that's 5 plus or minus. 25 plus 24 is 49, and the square root of 49 is 7. So 5 plus 7 divided by 4 is 3. And then 5 minus 7 divided by 4 is negative a half. Everybody's okay with that? Since these were rational, I knew that this was factorable, but who cares? You know, factor, use the quadratic formula, it doesn't matter. I think that that was probably going to be faster than factoring it, but who knows? We're not done yet, though, because we still have to check. And one of my answers gives me a problem here. If I plug 3 in for x, I get 0 denominator in multiple places. Everybody agree? So I'm going to discard that solution and only accept the negative 1/2. Happy there? This is coming back to us. What letter am I on here? As something we remember doing? Maybe. I don't know. So just like before, I'm going to start by trying to factor everything before I look for my least common denominator, since I have a piece that clearly looks like it's factorable. And in fact, it's the same factoring problem that we had a couple of times here. Apparently, when we were writing these notes, we really liked that particular quadratic. Oh my goodness. That is strange. Did you see it not picking up the 0.5 for whatever reason? Did it again? That's really weird. I don't know why I did that. Anyways. So I get this, I have 2.5s. 2.5 times x minus 1 plus 0.5 times x minus 3 equals x squared. And at this point, it might be tempting to say, hey, I'm going to multiply both sides by 2 to get rid of the decimals here. And it's okay to do that, but if you waited a couple of steps, you're going to find out that it really wasn't necessary, because all the decimals are going to work themselves out here when we distribute things through. Initially, that's what I did, and then I got to the next step, and I was like, oh, it would have worked itself out anyways. But, you know, it's no big deal. I'll move everything onto one side and combine like terms. So, are there two things that multiply to give me positive 4 and to give me negative 3? No. Okay, so I have to, in this situation, use the quadratic formula, but that's not a big deal. Negative 3 squared is 9, and then 4 times 1 times 4 is 16, for 2 times 1. And right away here, I notice that I have this negative number under the radical. So I'm going to just stop here and say no real solution. Because I know that negative under the radical makes it imaginary. Ms. Hannah? Certainly. Is that okay with everybody? So typically, for non-polynomial solving, we don't report imaginary solutions. So, and one last example is a story problem. Wee-hoo! What letter are we on? E or something, maybe? So Farmer Bill wants to fence in a rectangular pasture. The pasture must measure 500 square feet. Oops. What is the least amount of fencing he needs? So I would start just by kind of drawing a picture so I can get a visual of this situation, since it's like a real life situation. So there's my rectangular pasture. Let's pretend that's a rectangle. It's pretty janky looking, but so I'm going to call this side X and Y. So when we have a two-dimensional figure, there's two values that we can always say about it. We can talk about its area and its perimeter, which are two of the things that either we're asking about. The least amount of fencing would be the minimum perimeter. And then the area would be the size of that pasture. It needs to be 500, right? So I know the area for rectangle is length times width, and the perimeter is 2 times the length plus 2 times the width. So in our situation, we know that 500 is equal to X times Y, and then P is equal to 2X plus 2Y. Everybody's okay with what I did there? Okay. So what I want to do is I want to find the minimum value of P. So I'm going to resolve P. Right now, this equation with P in it has 3 variables. It has a P, X, and a Y. Can't do anything when I have one equation with 3 variables in it like that. So what I'm going to do is I'm going to eliminate the Y's by using the area equation. So I can rearrange the area equation to be 500, or Y equals 500 over X. And then I can substitute it into the Y in the perimeter equation. Everybody okay there? So now all I'm going to do is I'm going to solve this by graphing. So I'm just going to graph this function in my calculator. and then find the minimum value, or find the value for x when the y is minimum. In this case, perimeter is acting as our y. So I can say 2x plus 1,000 divided by x. And then I'm going to set a window. So if I'm thinking about x as one of these lengths of the fence, so I know a length can't be negative, so let's set the minimum x to be 0. Everybody happy with that? Okay. And then for a maximum x, I don't really know what that's going to be, but if the area has to be 500, if x is 500, y would have to be 1. That seems like a pretty dumb shaped pasture, and I can't imagine you'd want something that's longer and even narrower than that. So that's, I think, a reasonable kind of upper bound for the x. Does everybody buy that? I'm going to tell you right now it's going to be much less than 500. And then the y is the perimeter. So if I imagine this dumbest shaped pasture that's 500 by 1, that basically has a perimeter of 1,002 then. So I'm going to pick the maximum for the perimeter to be 1,000. And obviously the minimum, it's a perimeter, so it can't be negative, so I'll pick 0 there. And I'll hit graph and take a look at what I get here. So there's my function. So my minimum is right about here. That's what I'm going to be interested in finding. So I just want to find the x-coordinate at that point. To do that, I'm going to press second and trace and use the minimum command. So it asks me for a left bound, so I'm going to move my cursor so that it's on the left side of that point. Now, this little question is kind of in the way, so what I'm going to be really doing is looking at the y-coordinate. And as I move left, it should be decreasing till it gets to the minimum, and then it'll change to increasing. So I'm just looking at that y-coordinate, and when it starts getting bigger again, I know that I'm now on the left-hand side of that thing. So I'm just going to kind of keep snaking around here. And it started getting bigger, so I'm going to hit enter for my left bound. Now for right bound, I'm going to just press the right arrow and look at my perimeter. And once that starts getting bigger again, I know that I've gone on the other side of the minimum. So, or you could have reshaped your window. That would have been fine too. And then I guess it doesn't really matter. So my minimum value for x is 22.4. And the perimeter I'd have with that value of x is about 89.4. Everybody okay with that? Oh, hi, Father. How are you?
Good. Can I borrow you?
Yeah. Put my watch on it, though. I'm back.
Is it your birthday?
No, it's just that. So I think it's also teacher appreciation thing. So
Thank you. We appreciate it.
Yes.
that's very nice. Thank you. All right. The next section, we're going to talk about solving inequalities. So the idea here is if we have some function that's set like greater than 0, what I would do, maybe we have something, this might be our function, right? So if it's greater than, we're wanting to solve this greater than 0, we would want the x values that represent the parts of the graph where the function is above the x-axis, basically, right? So the only places where it can change from above the x-axis to below the x-axis are at the x-intercepts or at a discontinuity, like a vertical asymptote. So our process that we're going to use is we're going to find all the x-intercepts and vertical asymptotes, and then pick a test value on either side of each of them, and look to whether it's positive or negative. And that's going to basically be what we need. Does that kind of make sense to you guys? So we'll do a couple of examples here, because there's some tricky things that you have to kind of be careful about on this that I want to highlight in some of these examples. So again, this is a polynomial, x squared minus 4. A polynomial doesn't have any discontinuities. It's continuous everywhere, so all I'm worrying about are the x-intercepts. So to solve this, I can factor, and I get 2 x-intercepts, negative 2 and positive 2. Okay. Now, because this is an strictly greater than symbol, when I draw my x-intercepts, I'm going to draw them with an open circle. Just to remind myself that that point is not included in my solution set. And then I'm going to pick a test value in each of these little areas in between, segments in between my x-intercepts. So I'll pick, say, like a negative 3, I'll pick 0, and I'll pick positive 3. Now you don't have to pick these exact numbers, it doesn't really matter. You just need to make sure you're picking something on the left side of negative 2, something in between negative 2 and positive 2, and something on the right side of positive 2. So if I plug in negative 3, I get 5. If I plug in 0, I get negative 4. And if I plug in positive 3, I get 5. So the places that are greater than 0, which is what we're interested in, was this section and this section. Does everybody kind of see that? So to describe this section of the graph, I'm going to use an interval. So negative infinity to negative 2. And because this is an open circle, I'm going to remember to use a parenthesis rather than a bracket. took positive infinity, and again, because that was an open circle, I'm going to remember to use a parenthesis rather than a bracket. And that's my solution set. Is everybody okay with what I did there to get to that? We're going to do several more examples, so don't worry if you're still a little hesitant about this. I'm going to do, what, I think 3 more examples or something here. Because there's like weird things that we kind of have to make sure that we're being careful about. So. I want to do a variety here of examples of varying difficulty. So again, this is a polynomial, so I know that it's continuous everywhere, so all I care about are its x-intercepts. So I can factor that. I'll take out the greatest common factor, and then multiplies to give me 4, and adds to give me -4 is just x minus 2 and x minus 2. This time, since our inequality is a or equal to inequality, when I draw my number line, I'm going to use a closed circle. That's what that was supposed to say. You see, that's not very legible. I'm not sure that that was much of an improvement, but so far so good. And then I'm going to pick a test value from each of these 3 sections. So something left of 0 might be -1, in between 0 and 2 might be +1, and something bigger than 2 could be 3. So when I do this, I have, when I plug -1 in, I have -1, -4, -4, so that's like -9. When I plug 1 in, that's 1 -4 + 4, so that's 1. When I plug 3 in, that's 27 -36 + 12 is 3. It's positive anyways. So I'm looking for less than or equal to 0. I'm looking for this section and the number 2. Remember that 2 by itself was equal to 0, so it does need to be included. That's why we use the filled-in circle. So this piece, -infinity to 0, and again, since we're using a filled circle, that's going to get a bracket. And then union, this piece, because it's just a single number, I'm going to write with the set notation using the squiggly bracket there. Is that okay? So again, a little bit sneaky there. We had to be careful about remembering that the filled-in circle means it's included. So even though I don't have, it's not less than 0 anywhere else other than that far left section. It is less than or equal to 0 also in 2. Is that okay? So again, the overall process here is basically the same. We just have to be a little bit careful when we're kind of summing things up into our solution set. Oh my goodness, what did I do here? Try this. So my x-intercept is 4, and I have a vertical asymptote at -3. So the x-intercepts are going to get a closed circle because it's an or equal to, but the vertical asymptotes are discontinuities. Those are always open regardless of the type of inequality you have, because x can't have the value -1, right? That can't appear in our solution set regardless of what the inequality says. So the asymptoteness overrides the inequality symbol there. Everybody okay there? And why one is open and one is closed? So maybe we'll pick -2 from here, 0 from there, and 5 from here. So -2 gives me -6 over -1, so that's positive. If I plug in 0, that gives me -4 over 1. That's a negative section. And if I plug in 5 in, that gives me 1 over 6. So the positive sections are here and then here. Everybody okay with that? So this section is -infinity to -1, and because it's an open circle, it's a parenthesis. This section is 4 to +infinity, and because it's filled in section, per circle, it gets a bracket. Last example. Coming up. So here we have square root of x plus 4 over the absolute value of x minus 1. So my x-intercepts are just going to be -4. My VA is just going to be 1. Right? The radical part doesn't affect the x-intercept, and just the stuff underneath it has to equal 0. Same thing with the absolute value. It doesn't affect the vertical asymptote. You just need the stuff on the inside to equal 0. So nothing tricky going on there. And again, because of the inequality symbol there, I know all the circles that I'm going to write are going to be open. So I'll pick a value from over here, say -5. Value from in between, maybe I'll pick 0. The value from the outside out here, maybe 2. If I put -5 in here, I'm going to have the square root -1 over 6. That's non-real, so it doesn't matter what that is. That's neither greater than 0 or less than 0. I'm not including that section no matter what. If I plug 0 in, I get 2 over 1. So that's positive, that section. That would work. If I plug 2 in, that's the square root of 6 over 1. That's positive, so that will work. So greater than 0, we have this section and this section. So that's going to be -4 to 1. And those are open circles, so I used parentheses. And here we have 1 to positive infinity. Again, open section or open circle, so I have a parenthesis. And that's it, folks. That's the whole chapter, just FYI. So you guys should be able to do 25 to 57 here. That's the end of it. There are 2 worksheets in the content library. I don't need you to do them. I think that the homework set seems adequate. So I would say you can ignore those. Next time on Monday, do you guys have an AP exam overlap conflict on Monday? Or is that just fine to be like a normal, just get some work done day? I think it was Tuesday that has most of this stuff going on, it seems like next week.
Yeah, Tuesdays.
So I would like to try to do this test sometime next week, either Wednesday or Friday. So we can talk more on Monday about when to do that. But look at your AP schedule and see what's going on. If there's like a day that seems like, a lot of us are having AP tests, we can certainly move the test so that it doesn't overlap on that day, so you can give more of your effort to that. I know those are quite important, and I don't want to crush your day. You know what I mean? It's a stressful time of year, so I respect that.